A warm welcome to you all. After the break, we are proceeding for the project presentation. Great things are never done by one person, they are done by a team of people, Steve Jobs. So, we are having the project presentation of team 6 and 7 and then followed by open discussion and question and answer with our resource person, Dr. Pascal, for the clearing sessions. Over to team 6.
Good morning, everyone. Our project is about heart disease detection with machine learning. So, these are the contents, and what is heart disease? It is like about 32% of all deaths occurring globally. Heart disease is a major one. Around 18 million deaths annually, and types of heart disease: coronary heart disease, heart failure, arrhythmia, and what is coronary heart disease? It is like a blockage in the arteries, which the with a substance called plate. And what is heart failure? When the heart muscle itself would not be able to pump the blood to the body. And what is arrhythmias? It is like heart is beating too fast or too slow. And the risk factors from which we can identify this is high blood pressure, cholesterol, smoking, diabetes, obesity, all other factors. And early detection can reduce the mortality up to 80%. So we can suggest lifestyle changes or medication with detecting it early. And with challenges we are going to face is like our existing challenges like traditional diagnosis with PCG blood test is time consuming and costly.
This is our problem statement. Our goal is to develop a predicted heart disease presence using patient data. Why machine learning? Machine learning is a manual analysis of features like age and cholesterol is error prone and time consuming. Machine learning automates and improves accuracy. The applications are like early screening in hospitals, variable devices, telemedicine platforms. The challenges are imbalanced data. Then these are the objectives we have used in our project to study and pre-process the publicity available heart disease dataset to implement different machine learning algorithms for predictive modeling to evaluate and compare models using accuracy on a key performance metrics. So.
Yeah, so I'll be continuing the methodology part. So we have taken a simple like how to say machine learning algorithms. So these are the data set. This is the data set which we have used heart disease. I can show you from where I got. So this is the website where I got the data set. So here we have in total 303 instances, that means samples we have, and we have 13 features. So I can show you the features. So these are the features which we are going to use in our work. So we are considering age, sex, and some kind of cholesterol level, and whether the person has a chest pain or not, and some kind of things like I'm not into how to say clinician. I'm not a clinician, so I don't know a few of the variable names. So, like even the fasting blood sugar level is more than 120 mg, those things. So those are the features which we have used, and these are the. This is just a snippet of my code. So we have used UCMLR repository, and from there, ID number 35 is our hard disk data set where we can find, and these are the metadata of the data set. And so these are the features which we obtain. Everything is numerical values. Okay, we have not explored anything related to image, just a numerical. We have worked on numerical data. It had like few NAND files. So what we have done, we have removed the NAND files. classification approach. So we have in total 5 categories. One is healthy and 4 are like severity kind of things. Like 1, 2, 3, 4 like that. 0 is the healthy person's data and it is imbalanced. So 0 data is 164 and rest of the things 55, 36, 35 and 30. So we can see that it is imbalanced. For sure we are going to get the less accuracy for this. We tried to apply some small techniques also, but we did not like able to achieve good results here. This is just what we have done. So we have considered 80-20 training test related data, and 80% for training, 20% for testing, and just we have like worked on 3 algorithms. Like random forest, we just wanted to try the different estimators, like 50, 150, 100 we have taken, and this is just we have made it simple. And this is what we got, classification report and final result I can show you. This is our final result. These are our final results. So back to presentation. So that's what I just explained. So this is our data set overview and these are the features which we have used. And I explained which and all algorithms we have used and these are the results. Yes. So
I thought there was a timer. Like,
yeah,
wow. You guys are strict
so
today.
these are the results which we have. The human line thought. So thank you. Thank you. That's it. Yes. Yes. And yeah, we are 10. Oh, 11, including me.
Wow.
Yeah, we can have a photo.
Sure, yeah, of course. We doing questions first, or?
Okay, so any question, okay.
Or maybe we should do questions after, so we're all smiling. No, that's okay. It won't be bad questions. Anybody who wants to get started?
Yeah. So what are attributes can consider?
Yeah, that's what I do. Like, yeah, sex and other factors like the cholesterol level and those things like actually
How many are there?
So, yeah, that's your question.
Sorry, not 40.
Why the attribute is something like
I don't know. So they have publicly made it available. So yeah, these are the values which we got. I think before it was collected in 1988. At that time, I think they had a heart attack 29 and 77. But right now, I don't know. People say because of vaccination we get. I'm not sure about it. Yeah, because even I have seen that 4th grade student also had a heart attack. So that. Actually, I don't know these values. Sorry for that.
I can jump in here. So, I would say this is a good example of, how machine learning could help, right? You clearly showed it, it's correct. Like the performance was very poor. So, if you could explain to me how you would see this project progressing from what you've done, where you would be successful, or would you make it successful?
One is data casting, so we can improve the data, we can collect more data because as I showed, like samples are, how to say, it's very less, imbalanced data, we got whatever big data we had, we can see, so we can make it like, we can try to collect more samples and we can consider more features also. And we can apply feature selection because we have less features, so we did not do that part. And we can apply like augmenting the data, like not augmenting, we can try to like more techniques and all we can oversampling the data we can do.
Sure. So this is your outcome, correct?
These are the values. You want
Right.
to
No, that's your outcome, correct? That's what it's. That's a risk score. I'm assuming, correct? Is that a risk score?
no, those are the samples actually. 0, 1, 2, 3, 4. Those are the classes
The class of what?
of hard disease. I mean, 0 is the normal 20% sample,
One is-
and 1, 2, 3 are the mild moderate. I mean, whether they have a chance. I mean,
Right. So it's
yes.
That's what I said. Yeah. So it's a risk of developing a heart disease or having So you probably don't know, but there's a very, very large successful study in the United States called the Friend study that has done this like it's the gold standard of the world. So for risk assessment, we use what's called the Friend risk score. Versus risk based on almost the same thing. So my question would be, how could you improve on the framing and risk score, which would be very difficult, but it can be. And so my question is, how are you going to do that? Because really what you presented here is we use SVM in order to satisfy a linear statistical model, something that you could have done way before the machine learning, right? So there's no really deep machine learning stuff, right? But I appreciate what you're doing if you're trying to understand.
Just I wanted to the thing is, all of the students are new to this.
No, exactly. But that's why I'm asking you, is you got to show all your new students why you use machine learning. Because right now you haven't really shown them. You've just applied machine learning to a problem. Right? So then explain to me, what would you need to do, and why would you? What do you think machine learning is very I'll be calm. This is very hard. So how do you see machine? What is machine learning bring to this exact problem? If, as you say, the more data, I'm going to give you unlimited data. Do you need machine learning for exactly these variables if I give you 250,000 things?
Data can be data will be more, but how I can actually work better results like that.
Correct.
Okay, so one option is we can work on different machine learning algorithms.
So people select you're right. You're absolutely right. But for machine learning to be successful, you don't need samples to choose the features, right? So how can you leverage machine learning to be more successful? I'm a clinical expert as well, but why would you ever use machine learning? Because the previous numbers quote is actually very successful. It was an amazing experiment. I won't believe it, but it was an amazing experiment. So and working with a physician, you haven't been using for risk assessment. But you're absolutely right. Machine learning can help this, but you need to figure out what it is. So what have I said in the entire week that machine learning is really good at? What is machine learning very, very good at? Finding patterns. Sure. But it's the thing that we're dealing with what? Machine learning is really good for complex. Because you can deal with 14 variables. And you're going to say, pick the ones that are most important to do that for you. But what if you say, can you pick out 2,000 features, the ones that are, you can say, no, you can take a lot of money, I'm not doing that, right? Because the relationship between 2,000, acres is beyond his grasp, and I'm not insulting you. No. Right? Like, nobody can deal with 2,000 dimensions and more in his relationship in their head. So, the human can. So, what you need to do in order to escalate this to success, more features, definitely. More features with more features, because you get more features with more features. And so then how are you going to extend your ability for risk assessment? So now you have lots of features, very high dimensions, lots of patients. Now what are you going to do as a machine learner that's going to outperform this? So this is the basic to computer science. So what is it you can now offer me using machine learning? That's not. Now there's lots of features and lots of features. Non-linear relationships. Linearity is fantastic. And why is linearity so fantastic? Because we can understand that. Right? It makes sense. Like linear regression. Linear regression is you feel like, you go like this, that's all I need, right? So that's right. That is the coefficient, it's amazing. But how many relationships in real life are actually linear? Probably not that many. So to be able to model non-linearity in a very complex, high-dimensional problem is exactly where machine learning excels at. So I love your project because it's really the beginning, and what you demonstrated is why we need machine learning. Because if you stay here, it's always going to be fraught with machine. Right? We're not going to be able to turn right? It's something else. We're not going to improve on that risk assessment because we can't understand, the complexity of developing language, which is sadly a very complex problem. Because there are many ways, there are many reasons why you develop classes or things for learning, and that causes learning. And so this is only fairly, definitely some of the variables already diagnosed, so, wow, we don't, it's great. But what we could do is maybe, and actually people are doing it, but I would say, yeah, that's a good class. But just find data sets that are more complex, right, for sure, so that you can model these really nice models. But you're right, thank you. I know that is right? So it's so nice to be very right? But there are definitely more data sets that you can use. Sometimes that's where you collaborate with I mean, once again, the most problem, right? I want to know. Yeah, so exactly. So that's so it's a big part of the culture, right? But so you want to be able to assess risk, so you're going to have definitely genetics, family history, you're going to have to be environment, right? So I'm learning to do on nutrition, so again, all those, right? And not only just so smoking's bad, right? I'm telling you right now, smoking. However, when you smoke, how much you smoke, it doesn't have an impact. Because believe it or not, if you stop smoking, go ahead and just okay, just be ready to smoke now. Don't. But if you stop, it's okay, you do it. Like you will recover. Maybe it'll turn into smoke, but you can recover. So that's it. It's a thing on how much you smoke, when you smoke, if you stop. That's where the key learning is for sure. right? So anyway, that was thank you.
Good afternoon, everyone. I am Dhanushri from Group 7. We are here to present, present our project on dementia detection using machine learning and medical data. And our mentors, Srinath sir and Najib sir, and these are my group members. Introduction. Dementia is a medical condition where the person's memory, thinking ability, language skill, and decision making slowly decline. It is not just forgetting things. It is affect daily life like recognizing people, communicating, and doing daily tasks. Problem statement. Traditional diagnostic methods for dementia are time consuming, cost effective, and may lead to late detection. There is need for an automated, efficient, and accurate system that can predict dementia at an early stage using patient data and medical image. Objectives. Uh, our goal is to develop a ML machine learning model that can predict dementia at an early stage, making di- diagnosis faster, more accurate, and less cost compared to traditional method. A role of AI and machine learning in healthcare. Doctors may rely on scan, medical test, and medical history. If we use machine learning, large data set, and it can machine learning can analyze large medical data set quickly. In our project, we are used MI scan. It creates a structure of brain. It shows the size and shrinkage of the brain.
So I will be explaining about the methodology. So we used OSS MRI data set and we collected the data, and for data processing we converted the data into 224 by 224 pixel sizes. Then we did feature extraction, and for model selection we used CNN, which stands for convolutional neural networks. And for evaluation we split the data set into two, which is train and test. We did 80-20 and 70-30. So the challenges, we did not get enough data. When we initially came up with this idea, we thought to do with the audio and the text files, but we were unable to get the audio files. And data variability, since different hospitals use different machines and scanners, the data was inconsistent. And since dementia develops slowly, there are many minute changes, so it was very hard to identify. So overfitting risk. With small data set, the memory training failed on new patients, and the accuracy was also high. Instead of generalization, the model may start to memorize the patterns. And this is the tools and technologies we have used. We used the different libraries, and the applications are hospitals and clinics for clinical decision support, etc. So we split the data set into 4 classes, which is the mildly demented, moderately demented, and not demented, and very mildly demented. So this comes the code. So this is the results for 70-30 split. So this one is for 80-20. So here we came across a problem in our model. The accuracy nearly hit 100. That's because our model started to memorize the patterns instead of generalizing them. So this is the comparison table. So to conclude, I request Najib sir to take it.
conclusion, as my group members, they mentioned dementia is a serious and growing healthy problem. As they mentioned also, dementia is affect brain cells and make damage for these cells. Traditional methods for diagnosis of dementia is slow and expensive. AI and machine learning, especially CNN, can help to detect dementia earlier using MRI and text and audio data. Earlier detection means better treatment, better care plans, better lives for patient and family. Also, as Sir he mentioned for whole the program, the benefit of the AI and machine learning for diagnosis, earlier diagnosis, and cost effective, also faster diagnosis. So by using AI, I think the patient, they will lose the burden and can be impactful. Thank you.
Sure, great question. It's a very new, well, it's not new, but it's a developing area. And the reason it is because people have always avoided it, and now everyone's saying you have to have it, okay? So explainability is the ability to provide clarity and insight into how the model actually does what it does. So you can imagine if you have a linear model, linear relationship that's modeled by linear regression, then your ability to share with everyone how that model works is very easy, because you just need to provide the variables that are in the model and their coefficients. Done. The R square, we're done. Okay. But what if, next step, you have 2,000 variables in that model? Well, I mean, you can provide 2,000 variables and you can provide the weighting, the coefficients for the 2,000, but your ability to explain the model starts to become difficult, correct? So now let's move on to a nonlinear relationship. So the ability for us to explain a nonlinear relationship with that many variables is pretty much impossible. And so that's the reason, that's the black box, right? Is that it doesn't provide that information, right? It's just not, it doesn't give you which variables, because that's the other problem. And I don't want to get into too much stats, but you know, some of the coefficients are brought down to near zero, right? So meaning that they're not contributing. So our ability to even know that is because there's so many variables and so many relationships and so many levels that it's just difficult to even say which of the nodes are contributing the most. It's not possible to do that. So explainability is the ability to, an attempt, it's actually not even an ability, it's an attempt to provide some form of idea of what it's doing. So depending on how you model, there are methodological approaches that provide that idea of what's contributing what, how it's contributing, right? So SHAP, and there's a few, you can Google it, there's a few, ways to do it. But I think the easiest way for you to remember what you need to strive for is by what's called in parallel processing. So you have your model, which is fantastic, you're going to commercialize it, you're going to share it around the world, and everyone's going to be happy. But in order to perform explainability, you actually, mimic the process, right? So whatever your model is, but one with one that's explainable. So you're not saying that I'm going to get exactly the same results, because if that was the case, then why would you need machine learning, right? But you're going to get like similar results. But in doing so, you're going to be able to look in to that model and say, it seems to be more this area, these types of variables, this kind of process.
And that would be explainability in the sense that you're going to just transfer that to your model. So that's quite accepted. So if you're not doing Shapley and all that, doing the actual explainability methodology, which you can do, but you just can't always do that. Conceptually, that's kind of what is probably the most accepted currently, right? That might change, but for now it's just explain it as best you can using another process that you know is valid, of course, you're not making it up. And you're saying, well, in this parallel process, this is kind of what we think is going on, and so we're going to say that this is the same thing, but it's just more precise and does it better. Does that make sense? So that's explainability. Explainability is extremely difficult. That's the tough one. Interpretability is easier and is more relevant to the clinician. Because explainability gives certain variables, right? You're going to say certain variables are contributing the most to the model. So even if you do Shapley and those approaches, it's going to give you which variables contributed the most, which is what you need. But sometimes those variables are very abstract. And so then you're like, here you go. Here's my explainability. And people are going to say, oh, that's nice, but what's variable AZ15? And you're going to say, actually, I don't know. Oh, well, thank you for wasting everybody's time, right? So that's the problem. So interpretability is more important. And interpretability is the ability to share with your user an understanding of how your model came to the decision. So not how it operated, not how it is operating, not how it is weighted, how the nodes are weighted. No. How it came to the decision. So a perfect example of that is what students have already showed, and that is a heat map. So for in my world of imaging, it's a heat map. Because it doesn't get better than that. It's fantastic, right? Because you're showing on the image, where the algorithm, was paying attention in order for it to make its decision. So then, of course, if the clinician or whoever is using it agrees, then that's interpretability, because they're saying, oh, well, I agree with that process because that's where I would look to make my decision, right? So there's an example of interpretability, and that one is typically more important. If you're doing decision tree analysis and stuff like that, and it's very complex and whatever, so then interpretability would be to show an example or something on one. That's another one for interpretability is if you have a model, give an example, like give an exact example of one patient, So how did it come to what was the decision, how it made the decision for one patient or for 5 cases or something like that? That's interpretability. If you just give an overall value, right, like a performance metric, people don't really get that. They don't really understand, oh, wow, it works well overall. Okay. That's not really helping me. But if you give them an example of a patient, so here's a patient, Bob, kind of like in some of the, some of my students were giving in their presentation, actually it was me, sorry. Here's Maria that has this, and, compared to Carolina, which is that, that gives interpretability, right? Because you're sharing an example and how your model did what and what the decision was and all that kind of stuff. So that would be another form of interpretability. Yeah? Good? Cool. Any other questions? Yes? Okay, so complex question. You almost answered your own question with the last statement, which is ethical use of data and privacy, right? So your first thing, because that was very broad. IoT is Internet of Things, and so when you remember Internet of Things, remember data collection. Okay, that's what IoT is really all about, is data collection and use, Processing at site is edge computing, right? So when anyway, but your question is federated learning, which is for training models, right? And so as we discussed this morning, so excellent question. As we discussed this morning, the challenge, of course, is what data can you use when and where, and who gives permission, and how do you share, right? So the federated learning came around for exactly that purpose, and it's where people are like, well, I have a lot of data and I'd love to contribute, but I cannot share it. It's not permissible. I can't share it. I'm not allowed. Even if I de-identify or anonymize, it cannot leave my institution. So the thought was, okay, well, wait a minute. What if we all shared our results essentially, and people are like, oh, okay, well, maybe, but then how are we going to benefit from that? So that's when federated learning came along, where you can train in your environment, upload the weights. You're all working in, so basically it's a coordinated effort, right? So you all use the same model. You all, if you make a change to the model, everybody changes the model, right? So everyone's using the same thing. But then you train on your data, and then you upload the weights, and then that's shared for other people to use those weights and train with them, and everybody's training on the same weights and whatever. So data is not leaving your institution, right? You're just giving the permission for other groups in your federated learning, connection, to use what you did exactly the same way, right? Because that's the key, right? Is everything has to be the same, so that they can benefit from the weights. And then the whole group kind of does it all together, and in the end, ta-da, you have a fantastic model. Okay, that's federated learning. The problem with it, of course, is cost. So it's because what I just described is very simplistic, and I'm sure someone who's an expert in federated learning probably said, "Oh my God, that was terrible." But it's not as easy as that, right? And so you have to establish servers and privacy and connectivity and all that stuff for every site. And in Canada, the estimated minimum cost to get into federated learning is $25,000, right? So it's just a lot of money. And so most sites are like, well, yeah, if it's a huge project and it's worthwhile, then they'll do it. Or basically, if someone's willing to pay, okay, But if not, they're just not going to do it, right? And that's the barrier. It only applies, in my knowledge, to very well-funded, large pan-Indian, studies, right? Where all the major sites around India are collaborating, and they need to. So thinking about it at your level, or at my level for that matter, it's a waste of time. Like it's really, I mean, I'm just being blunt. You guys know me now after a week. I'm pretty straightforward. It's just such a complex and expensive endeavor for, I'm not going to say little gains, but, are the gains really, necessary, especially with foundation models now? People are willing to share foundational models. Wow, right? We can just benefit so much from that, right? Because that was the tricky bit, is how do you train on private data, right? So foundational models, people have agreed to share their data to train to a foundational model, and then those foundational weights or embeddings are shared. So you've solved the problem, because you can do the same thing now, right? So it's just that initial sharing that's the problem. If that initial sharing does not exist, like there's no way that anybody is going to share to create that, then you need federated learning. I'd be a very rich man if I knew that answer. And I'm working on it. That's one of my areas of interest. But no, there's no easy way of determining that other than being in the space. So been there, done that, right? So if you take on a new project, right? Let's say you're working with ultrasound in musculoskeletal disorders, right? So joints, right? And you're working in ultrasound, and you have a new project, and you want to know how much data you need. Well, you just call me. WhatsApp. Hey, Pascal, what's up? I know you're an expert in that area. What's your experience? And I'll tell you, absolute minimum 200 to 500 per class, right? And you can say, oh, wow, thank you. So how did I know that? Well, because I've done it for years. So I can tell you my experience. But even still, I could be wrong, right? Because maybe the ROI that you're interested in, you need more. Or it's so easy, like you need less. Right? Like in the back of the knee, Baker's cyst, right? You get this cyst in the back of the knee, which is a complication that you get ultrasounds of the knee done for, right? So you fall off your bike, you get an ultrasound done, they're looking for inflammation or whatever. Pain in the knee, arthritis, they're looking for arthritis. Pain in the knee, don't know what it is. Oh, it could be a Baker's cyst. Okay, so Baker's cyst is like, wow. You can't miss a Baker's cyst. Like, it's behind the knee and it's there and it's like, wow, I know. So, if you had to train an algorithm on it, first of all, why would you? But let's say you wanted to train an algorithm on it, it would probably be very easy. So then you would need less data. Does that make sense? Kind of. So in anything you do, it's going to be that, right? Definitely the work that my PhD student is doing may contribute to assisting people in estimating the size. But we wouldn't, you wouldn't use it for something really basic like, X-ray looking for, I don't know, even pneumonia or something, which is pretty straightforward. You wouldn't really need that. But for very complex MRI or CT or PET or something like that, very heterogeneous data, then what we're doing would be helpful, right, in giving you an estimate of what you need. Does that make sense? And that's going to make it harder. Exactly right. As soon as you start doing fusion, it's easy to remember. The more complex, the more data you need, right? So if you're doing fusion, you're going to need more data. Yeah, generally. I mean, if you can simplify it like we did using a scalar value, right? That kept the requirement lower, but we still had if I remember correctly, almost 900 CTs, brain CTs. It's still 900, right? It's not bad, right? It's pretty big data set. And so, it's generally, it's just going to increase your sample size. Any form of complexity will increase your sample size for sure. But there's no answer, no. Sorry. Any other questions? Yes, sir. Mm-hmm. What a great question. That really is a very appropriate question. It really is, and that is like, where are we going, right? So how are we going to incorporate this? So definitely. So I come from a software development background as well, and I started programming in the 80s, and then throughout the 80s and 90s, programmers were gods. They really were, because it was new, right? This whole concept of programming and creating software for computers was not very complex, but very difficult to do because of all the restrictions, right? So memory was the big one, right? So who controlled the environment? You did. You were in control. The programmer would say, this is what I can do for you. And you would say, oh, thank you, right? So that's no longer the case. Sadly, you guys missed that. Now it's the user. The user is absolutely in control. So the programmer must provide what the user asks for, even if, no matter how outlandish the request, you need to find a way to give it to the user or they're walking away. And the reason they can is because they walk away to somebody else who can do it. That's the problem. If truly nobody can do it, then fine, you're okay. But you do need to listen to the user. And so to answer your question, AI is going to be invisible. So ideally what it's going to do is not be seen, but to improve all processes. Like literally improve all processes. So is the physician going to be walking around with some kind of funky helmet and some weird, no. The physician is going to walk around just like they are today. Same way. But the tools that they have are all going to be integrated with AI. And the less anybody sees or hears or thinks AI, the better. That's going to be the goal for the integration of AI into what we do, is exactly that. It's just going to be, transparent. Like you're just not going to know. Having said that, there will also need to be like almost full departments for AI in the institution. So you're going to say, why do you need that? So is that going to be your job? No, actually it's not. So it's not going to be like a room full of programmers, in every institution just programming. No. What you are going to need to have are committees. So yeah, you think, oh God, more administration. But you really are going to need them. And those committees are going to be responsible for the integration and adoption of AI in their institution. So meaning you have to have a list of all processes in the hospital that are actually using AI, and they need to be monitored. So meaning they have to keep tabs on them. Because just as we talked about this week, you have data drift, right? You have this shift, right, in attention because the disease is progressing in society. The technology is changing on the variables of input for that algorithm. So these things change, and so then the accuracy of your algorithms are going to fluctuate. And so you need a committee, you need some kind of oversight that's going to check that. Is it still working the way it's supposed to? Should I be validating? Is it now unethical? Right? So think of that. Like, maybe today it's okay to do something, but in 6 months from now, or well, maybe in years from now, it's no longer permitted, or it is permitted now, right? So then your algorithm's out of date. So there's definitely going to need to be oversight in the hospital for exactly that. So then you're going to have this AI, committee and little group. Maybe you will have a few engineers, right? Why not, right? You have a few engineers that understand how it's done. And so they'll consult the committee and say, oh, that's interesting. Yeah, we'll have to retrain here. We have, whatever. So there'll be that. But the actual use of it is, in my opinion, this is all my opinion, of course, it's just going to be transparent. You're just not going to see it. You're just going to make, physicians are going to be using their phone more or their tablet more. They may have some VR goggles or something, maybe, for visualizing things in 3D. So they'll just, they'll just take it off. Actually, it's not going to be goggles anymore. Have you heard the, all of the hype, right, about the glasses, right? So Apple was supposed to come out with it, 4 years ago? Google came out with it like 5-6 years ago, the idea of AR glasses, right? Just failed. And it's just because the technology wasn't there yet and the adoption's not ready. It is coming. Absolutely, it's coming. Okay? And that physicians will be wearing. So physicians will wear glasses, and inside the glasses will be popped up information that they need real time. So if they're with a patient, if they wanted to, they could probably see some facts on the patient that will pop up in their glasses, in the inside of their glasses. But more realistically, will also be examinations. So for instance, if they're examining, if they're looking at like a skin lesion, right? They'll just look at the skin lesion, right? And the AI will, because there'll be cameras, right, on the glasses, right? And it will identify the lesion for them, put it up right in the, or maybe not identify, but just say, hey, whoa, pay attention to that, or something like that, to begin with. Eventually we'll identify. That's absolutely, I think, is going to be in our future, in the physician's future. I mean, why? Of course, right? Because then you don't even have to whip your phone out. You don't even have to, let me look at that, right? No, it's right in the glasses, right? So that's probably not far away that's going to be happening, because we're actually, my company is an Apple developer shop, and we've been asked to develop stuff for those glasses like 2 years ago. But we stopped because we just realized nobody's taking it up right now. So as a company, it's not worth our effort as a company to develop stuff that's just not being taken up yet. We're too small a company. If we were a big company, maybe, but we're such a small company, we can't spend time on that. But it's coming. Like I can tell you that's going to be coming. And you guys are going to wear it. I'm going to wear it cycling. So I'm a cyclist, and so when I'm cycling, I'm constantly looking down at my little computer on my handlebars, just to see where I'm at, how I'm feeling and where I'm going. But it already exists. It's just not for sale. In my glasses now will be all that information, right? It's going to tell me where I'm at, where my heart is, where my training status is, and all that kind of stuff will be in my glasses, right? So then I don't have to look down anymore. And then you're going to have the ability to detect stuff on the road and warnings, and you bet it's all coming for sure. That's cool tech that's going to be coming. And of course, it's going to cross over into medicine. Like, why not? Why wouldn't it, right? Like, that would be neat. That would be very neat, for sure. Good question, though. That's good. What else? Questions on projects? On your projects? No? That good, eh? So the only thing I can absolutely share in terms of the projects is, that was really a beginning, and I think you can do so much more, for sure. I am saying that in a nice way, by the way. I'm not saying, oh my God, that was terrible, do more. No. I'm just saying you certainly can progress and do more on your own. Like, you don't need necessarily someone helping you out. You can do it on your own. If you're a big enough group, everyone's going to think of something and you can do it. Having a little guidance from a prof or something is nice. It's helpful. But you can do all of this stuff on your own, right? So you should go to my website, actually. And so if you go to my website and go to student experience, I get that one. I get in trouble all the time because I work with students and I work with patients, and I'm constantly saying the wrong one. So if you go there, you'll get student experience. And if you read the experience, you'll read how they did exactly what you just did. Okay, so what you did, though, you did it in a week, right? My undergrads that are coming from engineering, just like you, computer science or whatever, they spend a semester with me, right? They do a credit, right? And so they'll explain to you on their personal experience, the ones that wish to put it on the website, of course, what was their thought process? How did they find it went? Was it hard? Was it easy? Whatever. And you'll probably appreciate their comments because it's probably exactly what you just went through, but they went through it at a slightly higher level because they were doing it for credit and they did it for a whole semester or a whole year. It's a year course, so they would do it for an entire year. And you'll just see it's all doable. I mean, there's a few tiers. It's pretty rare. Honestly, it's pretty rare. But sometimes it gets really stressful. Like, oh God, I'm not going to finish on time. I have literally, during these sessions and then when I'm driving here, no joke, I'm constantly talking to students because their project is due next week. So they're constantly asking, oh my God, my numbers are not right, and they're still running, like you guys, training data, and I'm like, that's not working, whatever. Anyway, so it does sometimes get right to the end, right? But in general, it's very doable. It's never easy. You'll see if you read the comments. It's never easy, but it's always rewarding, right? So just to say, that's the best part of it, and hopefully, this workshop will inspire you to do that. There you go. I think we're good, right? We're on time?